Section 2.4 is going to take a look at some applications of functions, specifically around the quadratic equation. So just to kind of set this up visually what we're talking about, I want to consider the graph of f of x equals ax squared plus bx plus c. And depending on what A, B, and C are, this graph is going to look like one of two things, maybe moved around, maybe a little wider, and maybe a little skinnier. It might look something like this, a parabola facing up, or it might look something like this, a parabola facing down. The way we tell the difference is if A is positive, if A is greater than 0, it points up like a smiley face, and if A is less than 0, it's going to point down like a frown face. What we're going to be specifically interested in today, though, is this point down at the bottom or at the top of the graph. Because what you should notice is that top of the graph is the maximum or highest point, and the bottom of the graph is the minimum lowest point. That point we call the vertex, which is either the min or the max, depending on the direction of the graph. And the way we can find this min or max is quite directly using the formula that the vertex of the x-coordinate is equal to the opposite of b over 2a. Notice it's the quadratic formula without the square root part. The opposite of b over 2a, that will tell us the vertex, or at least the x-coordinate of the vertex. And then the way we find the y-coordinate of the vertex is we simply plug that x point back into the function, and that's going to evaluate for us the y value. So this is kind of the big idea of today. You need to know how to do these two things and then be able to interpret them as well. So let's talk about the interpretation. The x-coordinate of the vertex tells us where or when the maximum or minimum value occurs. So if we want to know what value will maximize the volume of a box, we don't care about what the volume is, we just want to know when that maximum occurs. That's the x-coordinate. Versus the y value is what the maximum or minimum actually is. If we want to minimize our expenses, and I'm interested in what is that minimum expense, that's asking for the y-coordinate. So make sure you know what question we're asking. Are we asking when or where it's maximized, or are we asking what actually is the maximum value? So for example, we'll start with a really boring example that has no context at all. We're going to do f of x equals negative 3x squared plus 18x minus 7. If we want to know where the maximum of this graph is, we let the x vertex equal to the opposite of b, which would be negative 18, over 2a, and a would be negative 3. Again, we get our a, b, c, just like the quadratic formula, in front of x squared, x, and the constant, respectively. And so if we simplify this, we get negative 18 over negative 6, which is simply just 3. The vertex occurs when x is equal to 3. That's the where. The when. What is this maximum value? We plug that value that we just found of 3 into the function to find f of 3. So negative 3 times 3 squared plus 18 times 3 minus 7. And then it's just order of operations. 3 squared is 9, plus 18 times 3 minus 7. Multiplying gives us negative 27 plus 54 minus 7. And that is going to be 20, I believe. So the maximum occurs when x is 3, and that maximum value is 20. We'll never get an answer out of this function bigger than 20, and that happens when x is equal to 3. The assignment today takes a look at maximizing and minimizing lots of different application problems. Min-max problems. Now, I can't possibly go over all the different types of problems that you're going to see on the assignment without doing the entire assignment for you. Instead, I'm just going to do 4 examples that set up exactly what is going on with these min-max problems. Then your job on the assignment is going to be to take the context of the new problem, build your own equations, and go through the min-max process yourself. So first we'll start simple. We're going to find 2 numbers whose sum is 18 and whose product is a maximum. Looking at the information we have, we know we've got 2 numbers. So let's call those 2 numbers x and y. We know their sum is 18. X plus y must equal 18. And what we're asked to do is take their product and maximize their product. In other words, we want to multiply them together, x times y, and we want to maximize this. Well, we've got 2 equations, well, 2 parts. One's an expression, one's an equation. We want to maximize, so let's go back to that equation bit, and let's solve for one of our variables. Let's just solve for y. We can do that by subtracting off the x. Y is equal to 18 minus x. And what's nice there then is this 18 minus x, this constraint, can replace the y in our maximization. So we have x times 18 minus x. Well, if we distribute, that's 18x minus x squared. And actually, let's rearrange it, putting the x squared first. Negative x squared plus 18x. We now can find an a b, and a c, which is really 0, so that we can try and find this maximum. Notice this question is asking us to find 2 numbers whose product is a maximum. This is asking us to find when that maximum occurs. It's not asking us what is that maximum product. It just wants to know the pieces that make it a maximum. So here we're just looking for the x-coordinate of the vertex, which is the opposite of b, negative 18, over 2a, which is negative 1, or negative 18 over negative 2, which is positive 9. X is equal to a positive 9. So we found the first number now. The second number we can get by going back to that y equals equation. Y equals 18 minus x. And so we'll do that. The y equals 18 minus x, or plugging 9 in, 18 minus 9 equals 9. So the 2 numbers whose sum is 18 and whose product is a maximum are 9 and 9. Okay, that problem's really just a fun number game. Find 2 numbers who do this, maximize or minimize that. Let's do more of a application problem. Let's say a farmer is building a fence along a barn with two sections, as shown. So here's the barn. And the fence he's going to build is going to come out from the barn and go over, and then it's going to have a divider down the middle. So that's the fence. He has 100 feet of fencing. What size would give the maximum area? Well, we know area is length times width. And what's interesting here, as we maximize, that's what we want to maximize. Let's go ahead and write that maximization equation down. Area is length times width. That's what we're trying to maximize. But what I want to notice is that width is appearing 1, 2, 3 times. The length only appears once because we use the back of the barn for the other side. So we've got a length plus 3 widths to equal our total amount of fencing, 100 feet of fencing. Again, let's solve for one of the variables. Let's get the L alone because that'd be the easiest. No fractions is 100 minus 3W. And so we can take that 100 minus 3W and replace the L in our maximization problem. We've got 100 minus 3W times W. And very similar to the number problem we just solved before, when we distribute and put things in a different order, we have negative 3W squared plus 100W. Again, this problem is asking for what size gives the maximum area. When does that maximum occur? We don't care what the maximum is. We don't care about the area. That's not what the question is asking. The question is asking what is the size of the fence. So that's just the x vertex formula, which is the opposite of b, negative 100 over 2a, which is negative 3. And we're just going to round this to the nearest whole foot. Negative 100 over negative 6. So 100 divided by 6, it's a positive 16.6. We can actually do that, 16 and 2/3 foot. So that's going to be the W that we have here in our formula. We should have said the W vertex. The W is 16 and 2/3 foot, 16 feet 8 inches long. We still need to find the length, then that's going to give us, in the length we've got this formula, 100 minus 3W. 100 minus 3W. And if we change that back into a mixed number, or an improper fraction to make the math easier, that's going to be 50/3, which is really nice because the 3's divide out, and 100 minus 50 is 50 feet. And we've got our dimensions. 16 and 2/3 for the width, 50 for the length, and we've maximized our area alongside of the barn. So you notice the process is pretty similar here, is we end up with a couple equations, something that we're trying to maximize, Oh, I don't like that highlighting color at all. Something that we're trying to maximize with two variables quite often, but we can simply take this constraint equation, solve and substitute in to reduce it down to one variable. And it doesn't matter how complex or difficult the problem becomes, the process is still the same. So for example, if we were asked to minimize, let's minimize something ugly. Let's make it s is equal to negative 3x squared plus 2xy plus 4y squared, given some constraint that we develop, such as 2x minus 5y equals negative 9. Okay, this is going to get ugly. There's going to be fractions. The process is the same, though. We've got this constraint. We need to solve for one of the variables. Let's just go ahead and solve for x. 2x equals negative 9 plus 5y. Divide both sides by 2, and x equals negative 9 halves plus 5 halves y. So now we take this chunk and plug it in for our x. This time we're solving for the x. Why did we solve for x? Because I'd rather divide by 2 than divide by 5. No real reason. Both methods would give you the same answer. So now what we're trying to minimize is 3 times x, which is negative 9 halves plus 5 halves y squared, plus 2x, which is negative 9 halves plus 5 halves y, times y, plus 4y squared. So let's evaluate exponents first. We've got negative 3 times 81 fourths minus 90 halves, which comes out to 45. That's nice. No more fraction. Y plus 25 fourths y squared plus 2 times negative 9 halves plus 5 halves y times y plus 4y squared. Distributing through, the negative 3 and the 2 gives us negative 243 over 4 minus 135, plus 135y, don't lose that negative, minus 75 over 4y squared minus 18 halves plus, actually 18 halves, that's going to reduce to 9. Let's go ahead and just reduce that now. Minus 9 plus 10 halves reduces to 5. Y. Actually, I'm going to back up here. I want to notice we have to distribute the 2, but we also have to distribute the y through. So I'm going to treat that as 2y coming through. That way we've got the whole distributing. So it's going to give us negative 18y over 2, which again reduces to 9. If I can erase that 18. Negative 9y plus 5y squared plus 4y squared. Combine like terms. Before we do, let's get some common denominators here. On the y squareds, it looks like we want a denominator of 4. So I'm going to go ahead and do that. So the 5 I'm going to multiply by 4 over 4, and the 4 I'm going to multiply by 4 over 4. It's going to give us negative 243 over 4 plus 135y minus 75 over 4y squared minus 9y plus 20 over 4y squared plus 16 over 4y squared. Now when we add the y squareds together, we've got a common denominator, so we can add the exponents. Negative 75 plus 20 plus 16. Let's get a different color here. Combining the y squareds will give us negative 39 over 4y squared, plus the 135 minus 9 is 126y minus 243 over 4. Yes, there's fractions. Yes, it got ugly, but the process is still the same. What we've done is we took our equation and solved for a variable and plugged it into the original formula. A little bit of algebra makes it look like a quadratic, and so we can find the vertex. The x vertex, which actually is a y here, just to make it confusing, because y is our variable, is the opposite of b, negative 126 all over 2a, which is negative 39 over 4. I'm first going to simplify the denominator. 2 over 4 reduces to 2. And then, when we're dividing by a fraction, we're really multiplying by the reciprocal. So this is negative 126 times 2 over negative 39. And this is not going to reduce very well at all. A negative divided by a negative is a positive. I guess they're both divisible by 3. 126 divided by 3 is 42. 39 divided by 3 is 13. And that's all we're going to get out of it. So 42 times 2 is 84 over 13. This is the y-coordinate that starts to maximize. We can still get our x-coordinate. Going back, remember x was negative 9 halves plus 5 halves y. X was negative, I've already forgotten, 9 halves plus 5 halves times the y, which was 84 over 13. We're going to need to get a common denominator of 26. So let's multiply by 13, also the other fraction. So that's going to give us 13 times 9, which is 117, plus 84 times 5, which is 420, over the common denominator of 26. 117 plus 420 is 537 over 26. So that's the x, and that's the y that will minimize this function. So the algebra got ugly, but the process was still the same simple process. I want to look at one more example before we wrap up here, though, going back to real applications. Let's say we've got 100 tickets sold. To a concert. If the cost is $3 per ticket. Of course, if we raise the price, we charge more, we make more money, right? Well, the catch is if we raise the price, we lose customers. For every 10-cent increase in price, it is estimated that one customer would be lost. What should be charged to maximize our revenue? One thing we need to know about revenue is generated, how much money comes in, is the price times the number sold. So we need to look at how these factors are going to work together. The price, the initial price for a ticket is $3. We're going to increase the price a 10-cent increment. So we're going to increase 0.1, I'll even say 0.10 just to emphasize the 10 cents. We're going to increase 10 cents, but we don't know the number of times. So I'm going to call that x. So if x is 5, that represents 5 10-cent increments. If x is -2, that means we're decreasing the price 2 10-cent increments, or decreasing it 20 cents. So x is the number of increments, number of 10-cent increments. The number of tickets sold then, we're starting with 100 tickets, but one customer is going to be lost for each increment. So we're going to subtract one customer, 1x, for each increment. This now gives us something that we can maximize. Multiply this out, gives us 300 minus 3x plus 10x minus 0.1x squared. Combining like terms and putting things in order, negative 0.1x squared plus 7x plus 300. And then the vertex on x is going to be at the opposite of b, negative 7, over 2a, 2 times negative 0.1, negative 7 over negative 0.2. Move the decimal over, we've got negative 70 over negative 2, which reduces down to 35. What I want to be careful here, though, is 35 is the number of increments that we determined were appropriate to maximize our revenue. The question is asking what should be charged. The question is really looking for the price, which means to get the price we need to look at our price factor, which is 3 plus 0.10x. We just calculated x, so 3 plus 0.10 times 35 increments, and that's going to be 3 plus 350, or $6.50. If we charge $6.50, we're going to maximize our revenue. We're going to bring in more money than the customers we've lost. But once we go above $6.50, we'll start to bring in less money than the customers we've lost. So $6.50 is really the ultimate best price to charge to maximize our revenue. Today's assignment, the problems can take lots of different forms. They're all going to fall on the same premise that we find that minimum or maximum on the quadratic ax squared plus bx plus c by finding the opposite of b over 2a. You're going to need to use the context, the problem, and stuff you know to build those equations. Sometimes you'll have to do a substitution, but the process and the pattern is always the same. Take a look at the homework. We'll see you in class tomorrow.